Ladies and gentlemen, welcome. I would like to continue since didn't have time to finish up the material for lecture number 2. I decided to continue with a little bit more about polynomials, and then we will also talk about just a bit about functional equations. And if we have time, maybe I will do a little bit more about induction. Maybe you'll see an application, but probably I'll try to connect this with polynomials. Well, I will continue with a problem that we did last time, and that was, if I remember correctly, that was problem. That was problem B4, as you can see it here. This is problem B4 from 2003. And let me remind you that this problem reads as for the following. So we have a polynomial of degree 4. As you can see, it's written in this way. Az to the 4th plus bz cubed plus cz squared plus dz plus e. And well, we have the roots z1, z2, z3, and z4 are the roots of the polynomial. And if we know that z1 plus z2 is a rational number, and the sum is different, z1 plus z2 is different, is not equal to z3 plus z4, then we can infer that z1 and z times z2 is also a rational number. So let's look at this. Again, as you can see in the problem by just looking at the statement, it's quite clear that we have to use somehow Viet relations. And that's what we're trying to do. So keep in mind that the degree of the polynomial is 4. And what we're trying to do right now is to write the Viet relations. So let's write from the first Viet relation from the and let's write it. The first Viet relation is the sum of the root, which in our case is R1 plus R2, Z1, sorry. Right, okay. Z1 plus Z2 plus Z3 plus Z4. This will be nothing else than just, in our case, negative B over A. All right. So we know that this guy here, Z1 plus Z2, this guy is a rational number, right? So we know this. And we also know that the coefficients are integers, so therefore this is a rational number. So from here it follows immediately that Z3 plus Z4 is also a rational number. So we can deduce this very easily. Okay, now let's see maybe another relation also from Viet relation. And now we want to see a second Viet relation. And we want to use the second one, which is Z1, Z2. Z1, Z2 plus Z1, Z3 plus Z1, Z4 plus Z2, Z3 plus Z2, Z4, and the last one is Z3, Z4. Yeah, I think from this one, this is C over A, right? Okay. And now, well, we can group this together somehow. In fact, we can factor here. In fact, that's the secret of this. So this is let's call this first one Viet1, V1, and this is V2 from Viet2. And now we have to come up with some kind of a trick here to group these guys, because we know at this point we want to use the fact that we know that Z1 plus Z2 is rational, but we also know that Z3 plus Z4 is rational. So we want to use this information. So maybe we should do something about it, but also keep in mind that we have to prove that Z1, Z2 is a rational number. So maybe I should do something here. And if we look closely, we can do something indeed about it. So let's rewrite this relation V2 in the following way. And now we have to be very careful with what we want. So we have, let's write Z1, Z2. Let's leave them alone. And also we could put here plus Z3, Z4. And now everything else, so I'm just keeping this term and Z3 and the last term. And everything else, I can factor it very nicely. If you look, this will be nothing else than just C over A minus, and now I'll have Z1, Z3 minus Z1, Z4, it's minus Z2, Z3 minus Z2, Z4. Okay, that's beautiful. And because this can be factored easily, so this will be C over A minus, now let's be careful here. We can factor something, so we can have Z1 plus Z, let me see, Z3, okay. All right, so this is Z1 plus Z2 times Z3 plus Z4. Right? That's all right. We have this. That's nice. And finally, let's write the Viet3. So as you can see here, I have, since the degree of the polynomial is 4, I have 4 Viet relations, right, for the symmetric sums. As you can see, finally, we have the Viet relation. Let's call this V3. And this V3 will, this is nothing other than just Z1, Z2, Z3 plus Z1, Z2, Z4 plus Z1, Z3, Z4 plus C2, Z3, Z4. Okay? And this will be negative D over A. Beautiful. And now let's do a trick here as well, as we have done in the previous Viet relation in V2. This is equivalent with let's see. Let's be very careful here when we do this. Okay, so what I'm going to do is the following. I'm going to keep, okay, the idea is to keep this guy separate. No, not this guy, sorry. Z1, Z2, Z3. The idea is to keep the guy Z1 and Z2, this guy, separate, and Z3, Z4. As you can see, I have them here, and these guys, I have them here. And now, clearly, if we factor here, we have that Z1 plus Z2 times Z3, Z1 plus Z2 times Z3, Z4 plus Z3 plus Z4 times Z1, Z2 is negative D over A. Okay, beautiful. And now let's observe one thing. Let's observe that these guys, so observe that the products Z1, Z2, and Z3, Z4, these guys satisfy the linear system. If you look at them, right? Let's look at these guys, this guy and this guy. Right? They'll satisfy the following system. Let's call this S. And now, let's see, this is, let's say, alpha X plus beta Y equals U, and gamma X plus delta or sigma, whatever, delta Y equals V. So we have this system, they satisfy this system. And now let's see, who are these guys? Where, let's identify where alpha equals 1, in fact, is the same, alpha equals beta equals 1. Okay, gamma, yes, alpha, gamma is R3 plus R4, delta is R1 plus R2, and nu, U, sorry, we have, and U and V, let's write these guys. U is C over A minus R1 plus R2 times R3 plus R4, which is from the first, from the Viet2, and V is nothing else than just negative D over A, right? So keep in mind that, and that's the system. So we can rewrite V2 and V3 in this way. Yep. So this is a system of with two equations, two unknowns, and now it's quite clear what happens since we're giving the fact that Z1 plus Z2. Wait, this is, I'm sorry for the notation. I keep, this is Z1 here. Oh my. Okay. This is gamma is Z3 plus Z4, Z1 plus Z2. This U will be Z1 plus Z2 times Z3 plus Z4. Okay, and this is D minus. Okay, since Z1 plus Z2 is different than Z3 plus Z4, well, this system S has a unique solution. All right. It's and this solution is moreover, this solution is rational, right? This is important. And well, in particular, this means that both Z1, Z2, and Z3, Z4. Both of these two products are rational. And that's it. That's the end of the solution. Anyway, the problem is just a manipulation of Viet relations, and try to do some algebraic manipulations. At the end of the day, we end up with this system of two equations, two variables, and well, it's quite clear how this has a unique solution. You can express the unique solution anyway. You can use any method. You can use substitution. It's quite easy to solve this system. It's a 2x2 system. But anyway, what matters is that the solutions for this system are rational. So the unique solution is rational. All right. So this was a problem. I wouldn't say it was easy, but anyway, it was. Yeah, it was pretty straightforward. All right, now I want to do some other problems for, and the problem that I have in mind is the following. I'm not sure if I want to do something about irreducibility of polynomials, but anyway, the problem that I have in mind is the following. So problem. This was a Putnam B1 in 1985. The problem states the following. P of x is a polynomial. This is quite an easy problem, I would say. Of degree 5 this time, with 5 distinct integral roots. Okay. The question is, what is the smallest number of non-zero coefficients it can have? That is the question. And well, give a possible set of roots for a polynomial achieving this minimum. All right, so that's the statement. And let's explain it a bit. What do we want from this problem? I want you to look at it a bit. The problem is simpler than you think. Well, let's explain it a bit. Well, in other words, let us consider, let k be the smallest positive integer with the following property. So let's dive a little bit more into the problem. Right. And the property is the following. Let me write it with a different color so that you can see it better. The property P there are distinct integers. Let's call them M1, M2, M3, M4, and M5, such that the polynomial P of x, and we're going to write this in the following way. It's x minus M1 times x minus M2 times x minus M3 times x minus M4 times x minus M5, right? Has exactly k non-zero coefficients. Okay. So we need to find, in other words, we need to find a set of integers. And let's just say M1, M2, M3, M4, and M5, okay, for which minimum k is achieved. That's what we need to find. So that's the translation of the problem. Let's look at it. Basically, you see, it's the same thing. So that's what we need to do. And now let's analyze. It's actually simpler than you think. Let's analyze a bit. Let's see. For maybe let's look for, let's say for let's just see what happens if k equals 1. If k equals 1, then this polynomial p of x must be x to the fifth, right? But this guy, but p does not have 5 distinct roots. Right? Which are integers. Which are integers. Okay, so this doesn't work. Now let's see for k equals 2. If k equals 2, then let's consider this polynomial. P of x is x to the fifth. And now we're going to take another monomial, let's say a times x to the power r, let's say, for some non-zero integer a, right? Okay, and let's say that this r, the exponent here, is between 0 and 4, right? Okay. Well, let's look at this polynomial. If you look at this polynomial, let's analyze it a bit. Well, it's clear that P has 0 as a double root, right? If R is greater or equal than 2, for example, right? And not just that, but also, if we look at this, if R equals 0, also P has a non-real root if, let's say, R equals 0 and or R equals 1, for example. So we eliminated this case as well. And now guess what? Well, this implies that K is at least 3. And let's see, maybe for here we have an example. We can cook out an example. Yeah. And we can find the example is let's take this polynomial. So again, will be, let's say, x times x minus 1 times x plus 1 times x minus 2 times x plus 2, right? Or this can be written as x times x squared minus 1 times x squared minus 4. And if we multiply all this together, this will give you a degree 5 polynomial, which will be x to the 5th minus 5x cubed, I think, plus 4x, right? Yes, plus 4x. And this shows, in fact, that K equals 3, and that's it. Anyway, this was a very easy problem. In fact, you just had to inspect what happens for K equals 1, K equals 2, and then you'll realize that K equals 3. That's it. So this shows that K equals 3 is the right, is the answer we're looking for. Okay, now there was another problem that I had in mind to do. Let's see. For example, there was another Putnam problem. Yes, there was. Now I want to talk a bit about the derivative of a polynomial. And that problem says the following. I think it was a Putnam yeah, it was a Putnam A3 in 1991. That's a very nice problem as well, which says the following: find all polynomials with real coefficients, right, of degree n, and this is at least 2, with distinct roots let's say R1, okay, I'm going to keep the notation with R1, Rn this time. R1 strictly less than R2, strictly less than Rn, such that we have the following. the derivative of the polynomial p at ri plus 1 over 2 equals 0 for all I from 1 to n minus 1. Okay. I want you to look very closely at the problem. As you can see here, the derivative of a polynomial is involved, right? Well, the problem is not hard if we know the relationship between the derivative of a polynomial and the polynomial itself. And moreover, if we know that if we can express this in terms of the roots of the polynomial. And in fact, there is a formula. We will talk about it. But first, let's see. I know that, let's see what happens for degree 2. For n equals 2, we have that p of x is ax squared plus bx plus c. This is the quadratic polynomial. And the derivative is quite clear, is 2ax plus b, right? That's the derivative. And now, well, if we look at it, this means that we can express this in the following way. So we have that p prime of x can be written as 2a times, and now I'm going to factor here. I'm going to say is x minus b over 2a, right? Minus sorry. Okay, let me write it in this way so that it's quite clear. B minus over 2a. But we know from Viet relations that this guy, so this will be 2a times x minus, this will be, we know that b over a is the sum of the roots, so this will be r1 plus r2 over 2. So indeed, if it's quite clear, so the derivative evaluated, or r1 plus r2 over 2, will give us 0. Okay, so for n equals 2, it works. So, yep. So all polynomials of degree 2 will satisfy the condition. Now, perhaps we have a hunch that this will not be true for n greater or equal than 3. Let's see what happens for n greater or equal than 3. So assume that n is at least 3. Okay, so I know that the degree of the polynomial is at least 3. And now, and that the polynomial in Rx has roots R1 R2 all the way up to Rn. And we know that R1 is less than R2, less than Rn. Let's write it in this way. R1 is less than R2, is less than Rn. Okay. All right. So we know this. And now let's see how we can explore this. So we want to show, let's look at the statement again, that in fact, we want to show that for n equals 3, this doesn't happen. So let's see. So we have these roots, R1 less than R2 less than Rn. And now we know that we can actually write this polynomial. We know that that P of x can be written in the following way: a times x minus R1 times x minus R2 times all the way x minus Rn, right? For some real number a. Okay, and now let's denote this guy Ri plus, so denote the arithmetic mean between, let's say, two consecutive roots by R. Denote R, let's say Rn minus 1 plus Rn over 2, right? We know that P of R, since P of R is not 0, know that. Now we can divide by it. We have that we can, and let me write the following formula. We will use the following formula. The derivative of the polynomial P over P of R is nothing else than just 1 over R minus R1 plus 1 over R minus R2 plus all the way plus 1 over R minus Rn. So we have this formula. All right. But we know that R minus Rn is nothing else than just minus. So R minus Rn is nothing else than just minus R minus Rn minus 1. And so this implies that the derivative of the polynomial over the polynomial, this would be nothing else than just 1 over R minus R1 plus 1 over R minus R2 plus 1 over R minus or n minus 2. And this will be positive, right? Okay. And this implies that that the derivative cannot be 0, right? So clearly, there is no polynomial Therefore, there is no polynomial of degree at least 3 that satisfies the required conditions. Satisfies and that's it. So that's the end of the proof. So the only polynomials that satisfy the required condition are the quadratic polynomials. In other words, the problem was just an application of this formula. This is a must. You need to know that's how we relate the derivative of a polynomial and a polynomial. Okay, now I would like to say one thing about polynomials in arithmetic. It says the following. If I have a polynomial, let's say, and P is with integer coefficients, then P of x minus P of y is divisible, will always be divisible by x minus y, by x minus y. Well, it's quite clear. You just write the difference of the polynomial and you'll always factor an x minus y on that difference, and that's it's trivial. And also, another result that I want to mention is the following rational root theorem. Which says the following. If a rational number let's say P over Q with PQ are integers, Q is not 0, and the JCD between P and Q is 1, they're co-prime, right? If a rational number is a root of the polynomial, P of x a n x to the n plus a n minus 1x to the n minus 1 plus all the way a1x plus a0, right? And this polynomial with integral coefficients, then this happens. P divides the free coefficient a0 and Q divides an. So that's the rational root theorem, which is important. Anyway, we'll see some applications. I think one of the problems from the worksheet will require this at some point. Anyway, I'm not going to spoil it, and I'm not gonna say which problem is that. But all right. Now I think I would like to do one more problem with polynomials, and I think this problem was, well, it was quite easy, but anyway, It was a Putnam A2 2017. So which it's a more recent problem. Like I said, I'm gonna avoid solving problems during my lectures and recitations from the last 2 years, because I will devote this I'll devote to solving problems from the last 2 years to a special lecture. I think we'll have 2 lectures which will be devoted to this, to solving Putnam problems from 2019 and 2018. So I'll avoid during my lectures solving problems from the last 2 years. Anyway, now the problem says the following. It's a nice problem. Let Q0 of x equals 1, Q1 of x equals x, and we have the following, which looks like a recursion of polynomials. Qn of x is nothing else than Qn minus 1 of x squared minus 1 over Qn of x, Qn minus 2, sorry, of x, for all n greater or equal than 2. The problem asks us to show that whenever n is a positive integer, Qn of x is equal to a polynomial with integer coefficients. Okay. Let's look at this problem a bit. This has a the idea is quite simple. Basically, it's just induction, if you look at it. Well, but before we go, before we reach that part, we should try to linearize this recursion. And what we're going to do is the following. So let's look at it carefully. All right. So we have that. Let's write this for n. So we have that. Let's rewrite it a bit. Qn of x times Qn minus 2 of x in fact, let's write it this way. Qn minus 1 of x squared minus Qn of x times Qn minus 2 of x equals 1, right? It's trivial to see, even though it's 4 a.m. in the morning, but it's right. And now let's write this for n, right? Let's so this would be Qn squared, Qn of x squared minus Q of n plus 1, qn plus 1, sorry, of x, qn minus 1 of x. Okay, so we have this equality. And now this implies that well, the two are equal, right? That's obvious. But we can also write this as, let's look. Q okay. So we can write this as qn x plus qn minus 2x over qn minus 1x, and this will be equal to qn plus 1 of x plus q of n minus 1 of x over qn of x, right? This is the same thing. We just rewrite this. And now what we're going to do, we're going to iterate this. Once we observe this, as you can see there, if you look at it, you have n minus 2, n minus 1. You have n plus 1, n minus 1, n. So we iterate this equality. So let's call this star. So iterating star. And now we're going to get the following. So we're going to keep iterating for n equals 1, 2, and we keep going. We obtain. And now let's see, what do we obtain? Well, at some point, we will have that qn of x plus qn minus 2 of x over qn minus 1 of x will be nothing else. At some point you will have, for n equals 1, you'll have q2 of x plus q0 of x over q1 of x. And we know this. This will be q2 will be, it's easy to, q2 is what? Well, q2 is easy to compute. N equals 2. It's x squared minus 1 over, so it will be x squared minus 1 plus q0 is 1 over q1 is x. And this will give you x. Wow, wow. That's great. Hence, we have that, that what? That qn of x plus qn minus 2 of x is nothing other than just x qn minus 1 of x. Now, since q0 and q1 are both with integer coefficients, well, it's quite clear what will happen at this point. Then by an induction, and I'll leave it to you to do the details, it follows that that qn of x is also with integer coefficients for all n positive integers. And that's it. That's the end of the problem. You see, it was just algebraic manipulation. It wasn't that hard. Anyway, it was a Putnam A2. I remember, yeah, I was at Pitt at that point, and I remember some of my students had some problems in solving this. But anyway, it wasn't that hard. All right, I think I'm gonna stop here with the polynomials, but I'm not stopping here with the lecture. I would like to say a few words before I even I want to say a few words about functional equations. And maybe give you one example or a couple of examples. What is a functional equation? So let's roughly say the definition. A functional equation is an equation whose variables are ranging over functions. That's what it is. And we will see examples. Let me give you a naive example. Well, usually these kind of functional equations can be solved by just doing some substitution, by rewriting, iterating, whatever. They're not that hard. And I'll give you an example. So a problem where we can do this. And the problem is the following: find all functions let's say from R to R, and such that, and let's see, let me see an easy example, such that what? Let's say x squared times f of x plus, and now I'm going to do f of 1 minus x equals let's say 2x minus x to the 4th, right? For all real x. Okay, so this is a simple one. You'll see why. Because if you look here, why did I put all this? I mean, you have the variables x and 1 minus x. Maybe you should interchange them a bit. So replacing, so the idea is to replace x by 1 minus x. So replacing x by 1 minus x, we have, and let's see, what do we have? So we will have 1 minus x squared times f of 1 minus x plus, so 1 minus x is x plus f of x, and this will be 2 times 1 minus x minus 1 minus x to the 4th. Anyway, now I know who f of 1 minus x is, so I can just plug it in here. So since f of 1 minus x is nothing else than just 2x minus x to the 4th minus x squared times f of x, right? It follows that, so we're going to replace this in the given equation. And it will follow that. Follows that what? It follows that that what? Let's replace it. So it will be 1 minus x squared times 2x minus x to the 4th minus x squared f of x plus f of x, which is 2 times 1 minus x minus 1 minus x to the 4th. And now we do all this algebra together here, which is equivalent to it's equivalent to let's see, 1 minus x squared times 2x minus x to the fourth minus 1 minus x squared f of x plus f of x, oops, equals 2 times 1 minus x minus 1 minus x to the fourth. Anyway, this is just a matter of computations here, but I can see the function. In fact, let's anyway, I'll leave it to you as details. Clearly, this will give us f of x to be 1 minus x squared. Well, it's quite clear. And now, well, if you replace it, it's exactly what we need to verify. It's exact. So that is the, and now the last step is for you to check the equation. So you just have to replace this f of x into the initial equation, and you will see that it verifies. So if you look, x squared, so we need to check this. So we know that, so this would be an exercise for you. So f of x is 1 minus x squared. Let's check this. It will be x squared times 1 minus x squared plus 1 minus x squared, which will be and if you do all this together, it will give you 2x minus x to the fourth, which is exactly what we need. Okay, so that's good. Okay, so this is a very easy functional equation, but what I have in mind, and this is a must for you because we will do this when we will have when we'll talk about continuity. And the second, the other problem I have in mind is called the Cauchy functional equation. And I will solve this equation, but this is a very standard thing to do, but I would like to do it because this is important. Like I said, when we'll talk about continuity, you will see that this function equation will reappear. And it says the following, find all functions f defined on Q with values in Q on rationals such that this function is additive, which means f of x plus y is nothing other than just f of x plus f of y for all x, y, and q. So look at it. This is the Cauchy functional equation. What we're going to do will be the following. We're going to determine the function on the positive integers. Then we're going to go to the integers. And then at the end, we're going to go to the rationals. Well, if we want to pass from rationals to real numbers, and we will do this at some point when we'll talk about density, about limits of functions and so on, you will see that we will use the density of the rational numbers. Q is dense in R, and there will be some limiting process. But anyway, I'm not getting into details at this point. We will just determine the function on the rational numbers. All right, let's do it. And I'm going to do it in steps. Step 1, I'm going to show that f of 0 is 0. This is important. So how to show this? We take x equals y equals 0, right? Into the functional equation, and let's call this E, and plug in to the functional equation E. So what do we get? We have f of 0 plus 0, which is f of 0 plus f of 0. Or f of 0 is 2f of 0. And this implies that f of 0 is 0. All right, that's step 1. That's great. That was easy. Step 2. Well, step 2, we want to show that f of let's call this kx is k times f of x, right? For k a positive integer, a natural number, right? Okay. And x in Q. So we want to show this. All right. So we will prove this by induction. So we show this by induction. Over K. Okay. Let's see, for K equals 1, what do we have? We have, it's obvious. F of x is f of x, which is obvious. All right, now assume that this is, assume that this is true for K. And we want to see, and we show that f of k plus 1 times x is nothing else than just k plus 1 times f of x, right? So we want to show this. And now what I'm going to do is the following. Take kx to be y. And now let's see. And we have that f of k plus 1 times x, right? And now I'm going to write it in this way. So this would be f of kx plus x, right? And now I'm going to use the given equation. This would be, we know that f is additive, so this would be f of kx plus f of x, right? But by the induction hypothesis, I know that f of kx will be nothing else than just kf of x plus f of x, which is nothing else than just k plus 1 times f of x, which is exactly what we wanted to prove. Okay, great. So this is step 2. Step 3. We want to extend this from positive integers to integers. So what we're going to do is the following. So we want to show that f of kx is the same as k f of x for all k and z and x and q. Okay, great. Now what we're going to do is the following. We'll take y to be negative x, because I want to use the step 1 right now. And we get the following. We have that, so f of x plus y, it will be f of x minus x, which this guy will give me, and which is f of x plus f of negative x. But this guy right here is nothing else than just f of 0. But we have shown that f of 0 is 0. So this will imply that what? That f of negative x is nothing else than just negative f of x, right? So if we want to look at the negatives right now, and if I look at f of negative kx, right? And I know what this is. This implies that what? This is nothing other than just negative f of kx. But f of kx is nothing else than just kf of x, so this will be negative kf of x, right? For k and n. So at this point, it's quite clear that f of kx is nothing else than just k f of x for all k and z and x and q. All right, so we have shown this for integers, and now the final step. In fact, there is one other thing, one intermediary step. Let's put this step 4, and then at the end we'll see step 5. We want to see, we want to show that f of 1 over k is nothing else than just f of 1 over k, right? That's what we want to show. Well, that's easy. Take, let's say, x to be 1 over k. And we have what? Let's write this f of 1. This is 1 f of k times 1 over k, right? But now pay attention. This is tricky up here. This is f of 1 over k plus 1 over k. No. Okay, just a second, because I don't want to. F of 1 over k plus 1 over k plus 1 over k. And I have here k times, right? And this will be equal to f of 1 over k plus f of 1 over k plus f of 1 over k, which is k times f of 1 over k. And clearly now this follows immediately. All right. Well, here I have to do a little bit of an explanation. You can generalize the, if I have it for 2, f of x plus y is f of x plus f of y. You can have it for n. Anyway, that's not hard to see. And step 5, finally, we will want to use step 4 because that's the thing here. With step 5, basically, we want to show that every f of any fraction of this form will be nothing else than just m over n times f of 1. This is what we want to prove for mn in mn integers. Well, again, f of m over n which is going to mimic what we did earlier. And this will be nothing else than just, well, I'll leave it to you as an exercise to figure it out, that this is nothing else than m times f of 1 over n, which is going to make the same what we did earlier, but instead of 1 over k, we'll have we will have that instead of 1 over k, we will have m, 1 over n m times. So that's what we have, right? So this is easy to see. But we know that this guy is m from the previous step. We know that f of 1 over n is f of 1 over n. So this is m over n times f of 1. Okay. So in conclusion, it follows that f of x is nothing else than just a constant. Okay, let me put some, it's c times x, right? Or x in q. These are the functions we're looking for. And there is, you can easily check them. So the solutions to Cauchy functional equations are these functions, and this constant c is actually f of 1. Anyway, like I said, I'm not gonna dwell too much on the Cauchy functional equation, but what I would like to do, and you'll see it in various forms. When we will talk about continuity, you will see it. We'll see how we will use the density of Q in R. Anyway, now I would like to end up with the following problem. And this was a Putnam problem, which says the following. This was a Putnam B2 in 1971, so a long time ago. And the problem says the following. Okay, so the problem says let f of x be a real valued function defined for all real x. Let's just write the way it is, for all real x except x equals 0. And x equals 1, so it's not defined these points, and satisfying the functional equation. And the function equation is the following: f of x plus f of x minus 1 over x is 1 plus x. And the problem asks us to find all functions f of x satisfying these conditions. So this is how the problem was stated. Okay, let's look at the problem. Well, it's quite easy. It's basically very, very similar to the problem that we did earlier. We just have to replace a bit. Anyway, let's see. So clearly, we have to look at this guy, right? Because maybe I should find a way how to relate this guy to our functional equation. So let's set g of x to be x minus 1 over x. Let's set this guy. Well, this means that the functional equation can be expressed as f of x plus f of g of x equals 1 plus x, right? Okay. Let's see, what can we do from here? Okay, now if we iterate, right? If we so iterating, so I will just replace x by g of x, and I keep going. Iterating, let's say n times, we get the following. So I will have f of g of x, but this will be, and then f of g of x. So this will be f of g gn of x plus f of g to the n plus 1 of x. And here we'll have 1 plus g to the n of x, right? So this is what happens when we iterate n times. And now let's examine the powers of g, right? Because we know who g is. So these are the powers here. So let's examine the power of g. By examining the powers of g, we have, and let's see, what do we have here? So we know g of x is, let's see, g squared of x, because we want to see if we can we can find a recursion. So g squared of x will be so this would be, let's see, it will be x minus 1 over x minus 1 over x minus 1 everything over x, and this would give us, oh my god, exactly this one. I don't need this to do computation at 5 a.m. in the morning. So this would be, actually it's easy, it's 1 over 1 minus x. Okay, great, that's actually great. And let's see, g cubed now. So g cubed will be g of, now it's nice, 1 over 1 minus x, which will give us, well, this is, let's write it here, which is 1 over 1 minus x minus 1 over everything over 1 over 1 minus x. But this will be equal to, and surprise, surprise, x. Oh, it's x. Nice. Yes, right? Okay. Well, it's quite clear at this point, since g cubed is x. Okay. Now, let's call this star. So I know that g cubed is x. Well, since g cubed of x is x, by applying star, we get the following. Let's see, what do we get? We'll get that f of x plus plus f of g of x plus, and now this guy will give me, and we should be careful here, and actually it's minus, so this would be minus f of g of x plus f of g squared of x and it's plus plus f of g squared of x plus f of x, right? And this will be equal to, let one g to the, oh my g cube, this will be equal to 1 plus g of x plus minus, sorry, minus 1 plus g squared of x plus 1 plus x. Okay, I think that's it. I hope. And now let's clean this up. As you can see, everything just this gives us, it will give us the following. It will give us that 2f of x equals 1 plus g of x minus g squared of x plus x. That's, and now it's quite clear that f of x is nothing else than just 1/2 times everything 1 plus g of x minus g squared of x plus x. And now we know who g of x and g squared of x are, and I'll leave it to you as an exercise to finish this off. And that's it. That's the problem. Anyway, the function is, I don't know, it's a rational function, and you can verify that this indeed very satisfies the functional equation. Anyway, as you can see, it wasn't just iterating. That was the idea, and then just computations. All right, guys, I think I'm gonna stop here for today. So we will have on Thursday, we'll solve some of the problems from the worksheets, from the worksheet number 1 actually, and these problems will involve the polynomials. Some of them are will concern some sequences. Most likely we will use induction. And that's pretty much it. We'll start next week talking about geometry. Anyway, thank you very much.